Good afternoon, everybody. I'm very happy, actually, to be in such a wonderful place to talk to you about the ENUBET project. So, in a nutshell, ENUBET is a project whose goal is to demonstrate the technical feasibility and the physics performance of a new kind of neutrino beam, in which lepton production at high angle could be monitored at a single particle level. So the goal of the project is basically to produce a beam with unprecedented control in the normalization of the flux with a program on cross-section, as I will explain later. So it is based on two pillars. First one involves to build and test a demonstrator of the instrumented decay tunnel. And the second one is to simulate and design a suitable hadronic beamline that is capable of achieve this kind of goal. So I will present our most recent, the status of the art of the project. So the advancement in the simulation of the beamline, accelerator studies with SPS, and also our program of R&D for detector development and prototyping. ENUBET is funded by the ERC, and it gathered a significant number of people interested from 12 institutions, which are mainly Italian universities or INFN sections, with contributions also from CERN, Zagreb, and INR. So we are particularly proud of having been also recognized as a project in the so-called Neutrino Platform. It is a kind of container of R&D for a neutrino project at CERN. It's the same one that involves the construction of the prototypes for dunes, for example, or the detector of T2K. So we have collaborated constantly with CERN. So this is a kind of recognition of our work. And now, actually, we are also refereed by the SPSC committee. So, but let's come to the physics idea of ENUBET. So you know that the production of artificial neutrino beams is plugged by significant systematics on the normalization. And this comes from the fact that the process by which artificial neutrino beams are produced involves a quite complex chain coming from protons impinging on a target, and then all the simulation of the hadron production, the secondary reinteraction of these mesons on the aluminum, on all the passive things. And then this turns out in the fact that basically you deeply rely on simulations. So your flux is affected by uncertainties that typically range from the 5 to 10% level. So the change in perspective that we are proposing is to focus not on the hadron production, that is still useful, but not sufficient in our view, but rather to concentrate on the decays that are, in some sense, what is the closest observables to the produced neutrino events. So the idea is to instrument this region that is usually passive, because it's a quite difficult region in terms of rates and irradiation, and turn it into an instrumented volume in which you can monitor, in particular, the emission of large angle positrons from, in particular, these KE3 decays. So why this? Because, as you know, the NUE cross-section is particularly crucial for the program of future neutrino physics. And also because the idea is that you exploit the fact that kaons produce secondaries at large angles. So in principle, you would like to have a very well-defined beam, such that the only thing that you see in the tagger is not the primary meson beam, but just the decays. So especially the kaons are the ones that have larger acceptance, because due to the mass, decay products are ejected at larger angles. Okay, so ENUBET could be the base for a new kind of facility, which could have a central role in the future landscape for of neutrino physics, in particular by providing a way of measuring very precisely the new cross-section. This would help greatly the reduction of the systematics budget in the CP violation program, and also would help maybe in studies of more exotic phenomena like sterile or neutrino non-standard interactions, in which the knowledge of the normalization is particularly important. So this is how the setup would look like, more or less. So you have the protons impinging on a target, then you have the hadron production, and then this is the so-called beamline. It's a collimation in which you select a particular region in the phase space, so you momentum select your secondaries, and then you have this beam of pions and kaons that goes through this tagger, and then the decays are monitored by this, that it should be like about 40-meter length region equipped with detectors. The kind of the detector that would suit this program is a moderate mass detector of about 500 tons. It has to be a good ability to separate electron neutrinos, because this is a beam that is comprised of muon neutrinos and electron neutrinos. So, for example, a detector like Icarus at FNAL, or the proto-dunes at the North area at CERN, or even a water Cherenkov detector at JPark could play this role. So here is more or less the work that we have done. So we are doing a site-independent study. So we are considering the possibility of building this facility at CERN, Fermilab, or JPark. We use FLUCA for target proton interaction simulation. And then as comes from the focusing, we have a kind of two possibilities. The first is to use a horn. There is a PASS device, as you know. So in this case, you would need to have your protons synchronized with the horn. This is quite interesting because the horn has quite good collection efficiency, and it does also has drawbacks, as I will say. The other possibility is to use a static focusing, like what is shown in this picture. That's to say a quadruple triplet here and one there. So in this kind of game, we have to keep this part short, such that kaons that this energy of about 60 meters of decay length doesn't decay too much. And basically, we found out that the proper momentum is at about 8.5 GeV with a spread of about 10% to produce the kind of neutrino spectrum that would be interesting for physics. In all this design, we have been quite conservative in the sense that all these magnets are something that has already been done. So we, by construction, we didn't work with large extrapolations. Okay, this is the results of detailed simulation of the beamline. So here you see a comparison between the focusing system and the static ones. So you see that with respect to the proposal, that is a paper that was done in 2015, we realized that the horn was a kind of underestimated by a factor 2 in terms of efficiency, while the static option was even more underestimated. So this option gained a lot of momentum because it was disfavored initially because we were saying it will not give enough neutrinos in the time that we have. Now things are a bit changed. Also, in view of the fact that a static extraction has several appealing features. For example, you don't need a fast cycling horn, which is something that technically is thrilling. And furthermore, if you can dilute your protons with time, you basically mitigate a lot the problem of the pile-up in the tagger. So you are working in safer and easier conditions. So in this way, you can also consider the idea of operating really a tagged neutrino beam. So not just a beam in which statistically you monitor the flux by measuring on a statistical level the positron spectrum, but really to be able to correlate a neutrino interaction in the neutrino detector with a decay of a decay product of the parent of the neutrino. Okay. This is the kind of spectra that we expect after about 1 year of running over a detector, as I said, with a mass of about half a kiloton. That is in line with existing detectors already. So this detector will be at about 50 meters from the end of the tagger, so rather close. So you can see here that here is the muon neutrino flux, is the electron neutrino flux. The muon neutrino flux is composed of a low energy component from pion decays and a high energy from kaon decays. So this is an interesting feature that is, comes from the fact that the parents are very momentum selected. So it's a feature of this kind of narrow band beams. So basically, while for the NUE, you see that the only source is a three-body decay of kaons. You see that the numbers are rather large. So in principle, statistics is not an issue for this kind of experiment. So in particular, you see that the NUE are by 98.5% composed from, arising from kaon decays, that are the component that we are trying to monitor. And only a subleading component from muons. This is due to the fact that the tunnel is short enough not to let the muon decays and disturb you. So another interesting feature is that if you look at the interaction of the neutrinos at the detector, you see that if you plot the radius in of the interaction point with respect to the neutrino energy, you can slice your interaction depending on how far they occur in the center of the detector or far away. And by construction, so to say, you select narrow regions in neutrino energy. So you see here, for example, you go from red to blue to red to blue to red, green to blue to red, just changing on this variable, which is quite easy to reconstruct. So in some sense, you can bin in R and get a very precise information on the initial energy spectrum. And this is for sure very interesting when you're trying to do cross-section measurement, especially in beams of energy. Coming to the systematics, this is one of the major works that we have still to do. I just sketched which is the idea. So basically, the idea is that you can constrain the neutrino flux by doing a counting of the K3 decays, with this proportionality factor being related mainly by the geometry of the detector and the kinematics of the decay. That is a much easier task with respect to the task of wanting to predict the neutrino flux from the other production. So the idea is to isolate the K3 decays, so you have to reconstruct the positrons in your tagger. But even we have another possibility, that is to use a kind of silver sample. That is, that means measuring overall the kaon production rate in the kaon multiplicity in the tagger, and then relying on the brushing relation of the K3, which is anyway known with exquisite precision thanks to the long all the kaon experiments in the past. So we are trying to pass from these semi-qualitative statements to an analysis. And so the idea would be to make a kind of covariance matrix of the flux, then fit it with the rate of the positrons, and then by doing this, constrain the uncertainty on these parameters that modulate the normalization of the flux in each beam. So we are also extending a bit the initial scope. The fact that we saw that this static focusing is very promising led us to think that maybe even the low energy muons could be constrained. And so this is not possible in the tagger because, as I said, the larger acceptance in the tagger is for kaons. So what to do for the low energy pions? One idea could be to place these absorbers under the hadron dump, instrument them, and measure with range the momentum of the produced muons. So you see that there is a strong anti-correlation between the spectra of the muon and the spectrum of the corresponding neutrinos. So we plan to put this information in this machinery to constrain also the muon neutrino flux. So we have identified possible detector technologies, and we are in the process of putting these into the machinery. As you see, pion decay products are very forward, while kaons 1 are measured in the tagger. So here I present you a very significant advance in the design of the beamline. So formerly I showed you a beamline that was our previous baseline option that had a bending angle of about 7 degrees. Actually, we have improved this scheme by adding a second dipole. You see first dipole here and second kick here, such that this brings to a doubling of the angle. So this has several advantages. So some of these advantages also, for example, this is a bit longer, but the quality of the beam is much better. Here you see the momentum of particles as they enter the tagger. So these are the particles with the right momentum, and this is all the things, unwanted things, large angular momentum. This is significantly better than before. And in doing this, we have also improved a lot the shielding. So we have reduced significantly the amount of high energy muons that were punching through inside the tagger. Here you see a rendering of the way we intend to the shielding. And in these plots, you see that how the situation improved just by improving a shield in front of the tagger. So this is a big tungsten block with a conical shape. We optimized the radiuses of these two entrance and exit. And so you see that by doing this, you keep basically all these particles that are the interesting one for the neutrino flux. And you kill by several factor 2 or 3, all the backgrounds that are in this low energy region for positrons, protons, gammas, pions, muons, generally with some increase here, and almost everywhere for neutrons. Another very important step forward with this design was the fact that basically by increasing this angle, you reduce this component of electron neutrinos that comes from early decays near the target, especially from K0 long. So you see that if you make a cut on energy, you get only this red part, that is the component of electron neutrinos that arrive at the far detector and are also produced in the tagger. So they are the one that we can constrain. And this is much better than it was before with a shorter angle. You see that there is still a component of neutrinos that are produced here upstream that are not taggable, that will have to be corrected with a simulation. As I said, we are also considering the possibility of using a horn focusing. So we have collaborated with colleagues at the CERN SPS extraction group to envisage the possibility of making an extraction in which you squeeze the protons in bunches to be in sync with the pulsing of the horn, but still not to be like a fast extraction, which you have like a microsecond or 10 microseconds that would completely swamp your instrumentation. So this was generated interest in the specialists of accelerators, and it was successful. You see that you can transform the usual slow extraction spanning several seconds in like a combo in which all the protons are squeezed. And most importantly, it was found out that this does not introduce too much radiation losses to the accelerator, to the electrostatic septum. So this is actually also implemented in the control room. So it was a kind of successful spin-off also of the ENUBET. So as I showed you before, the horn is, from early estimates, already quite more efficient. But we are now trying to resume this work of optimization. So we are setting up like a very systematic search for the optimal solution by exploring parameter space and looking at maximizing figure of merit that is likely the number of kaons with the right momentum in the exit of the horn. This could replace actually the first triplet, so it would shorten the beamline and ensure even more statistics. So we have simulated the beamline with various tools. This is, for example, Fluka that allows us to estimate the radiation damage to the detector and the neutron irradiation. We are also benchmarking our simulation. We use Giant4 beamline for design. We have reproduced everything with Giant4, so we have get a good agreement. And most importantly, we are able to map the origin of the background. So this will be useful in a further tweaking of the design to reduce even more the background. So this is the idea for the tagger. It's basically a segmented calorimeter that has to separate shallow angle positrons from pions that are abundantly produced, for example, from other kaon decays. So this sampling calorimeter is complemented by a tracker made of doublets that is used to reject pi zeros that most of the times doesn't leave any signal in the doublet, but just shower in the iron. So it's an iron scintillator calorimeter. These are the input rates that we expect. So you see, this is the Z along the tunnel. So you have a kind of flat contribution from muons, and while this is what we want, so the contribution from kaons, and this is some unwanted contribution from pions. I remind you that pions are like the majority of the particles that enter, so having this quantity is already a big achievement. This is the input. Then we have the reconstruction in the tagger that selects from these products the positrons. So concerning the rate, we are in a good situation because we see that we get at more at 0.5 megahertz per channel, and up to 1 megahertz, basically there is no drop in efficiency using digitization with 250 megasample per second. So this is the result of an analysis of waveforms in which you deal with pile-up effects. So now I describe something about the positron reconstruction. So the analysis is done in several steps. The first one is to cluster the events. This is a kind of as a display of the pattern of positrons. So you basically identify a seed and then you cluster cells. I don't want to go too much into the details. Then once you have this cluster, you build a neural network from several 15 variables that describe the pattern of energy deposition in the calorimeter. And you select, you throw out all this green part, that is the pions. And you're only left mainly with the decay products from kaons, that are these yellow. Further step is to select, throw out all the pi zero and only get the K3. So I make it short. This is the final result. So you see that this dark yellow is the signal from K3. So with an efficiency of 24%, half of which is about geometrical due to the fact that there is a hole in forward, we get a signal to noise of about 1.6. And this is a big improvement with respect to our previous beamline. You can also decide to work at somewhat lower efficiency, and you get a signal to noise of about 3. So even in this setup, thanks to the slow extraction, you could think to make time coincidences. So in these conditions, with this kind of extraction and 20% efficiency and a signal to noise 1.7, you expect one candidate every 77 nanoseconds and a background every 130. So if you assume these figures for the resolution of the tagger and the neutrino detector, which is not impossible, you get that already you can do time correlation with getting the right positrons in most of the times. So I speed up. The last part of the talk is all the R&D that we did on calorimeters. The first attempt was to use silicon PM embedded in the calorimeter. So with the fibers that are running in this direction and the boards with silicon PM inside the calorimeter. So this is a setup that we tested at CERN. And we demonstrated that this detector is doesn't move on. Also, the detector was performing very well, and we were quite happy. It's very elegant and compact. We have also considered other possibilities using, for example, like kind of polysiloxane-based detector in place of the standard silicon, the plastic scintillator. And this also was recently published. So I'm forced to go a little bit further fast, sorry. Also, the Photon veto was tested, and it is in line with our expectations. So it was basically validated, this kind of detector. What came at a certain point is the effect of neutron irradiation. So we made exposure at INFN Legnaro, which is also a nuclear lab near Padova. And so basically we exposed this silicon PM to rates that are expected in the experiment. And we saw, of course, a deterioration of the noise. But we concluded that still the signal from the minimum ionizing particle could be distinguished from the pedestal, even this irradiation, even though, as you can see from this picture, the safety factor is not tremendously reassuring. So basically, we have moved to another design in which the silicon PM are not anymore inside the calorimeter, but are brought away by about 30 centimeters with a shield made of borated polyethylene. And this, from simulation, would allow a reduction of about a factor 20 in the neutron fluxes. So this, then we realized a detector based on this concept in which the light, instead of being red inside the iron, was brought up with wavelength shifting fibers and read in groups of 10 by silicon PM. So this is an even larger prototype that we exposed at CERN. And based on this know-how that we completed, this is the kind of object that we are in the process of building. It's called a demonstrator, so it will be about 3 meters in length, and the goal is to demonstrate the physics that it works, and then that is scalable and most importantly cost-effective, because the idea of the detector is to be quite extended. So now we are in the process of making an engineering of this object. So we are procuring scintillators with proper shapes, silicon PM, and also thinking how to do the mechanics of this object. Another important step is that we are building the electronics. So again, to have a cost-effective solution, we are doing it custom electronics. So now we have a first prototype with the 4-channel. And here you see things seems to work well. You see digitized waveforms with these custom electronics. So I'm done. The program overall is going quite well. We have also some positive surprise. Of course, we are fighting with the background, as any other experiment. It's just a conservation law. And as I've shown, this double dipole beamline is a very good step of the project, because it allows to have a single particle positron monitoring with a rather good signal-to-noise ratio and a reduction of the untagged neutrino component. This lateral readout is our baseline now, and we have also had progress on the development of electronics, and we are proceeding to the engineering of the prototype. Next steps is to complete the work on the assessment of systematics, build this demonstrator prototype, and deliver a conceptual design report of this kind of facility, with the hope that this would attract the interest of the community even more, and maybe could be like a first step for a larger experiment based on this technique. So thanks. Sorry for being a bit long.